Good morning, dear students. Today we are going to discuss about the crystal field stabilization energy and pairing energy. The splitting of the d orbital in a complex. We have discussed the splitting of the d orbitals in a complex in the presence of the ligands. The splitting takes place depending upon the geometry of the complex. If it is an octahedral geometry and tetrahedral geometry, all that we have discussed it. So the splitting of the d orbitals in a complex, the system gains an extra stability due to the rearrangement of the d electrons. Okay, so in the case of octahedral splitting, we have mentioned that suppose if you take a d orbital, so if you take d orbitals in the presence of the ligands, isolated gaseous state, all the d orbitals are having equal amount of energy. They are degenerate. In the presence of the ligand, these d orbitals energy is excited. So as the ligand approach, the d orbitals will be, now this is a isolated gaseous state. In the presence of the ligands, the energy is increased, and as the ligand completely approach, they are split into two levels. So that levels are, we know that in the case of octahedral complexes, they are split into 2 Tg and Eg. Now 2 Tg means dxy, dyz, dxz. Eg means dx square minus y square. And we also have calculated the crystal field stabilization energy, that in the presence of electron in the T2G level, will stabilize the complex to the extreme of 0.4 delta O. 0.4 delta O minus 0.4 delta O. And the presence of the electron in the Eg orbital, that is dx square minus y square or dz square, the presence of an electron in Eg level will destabilize the complex to the extent of 0.6 delta O. This stabilization is called crystal field stabilization energy. Crystal field stabilization energy. Though they are split, the barycenter remains unaltered. Okay, so now we know that always electron prefer to occupy ground level. That means lower energy level. If evidently, suppose you take D1 complex. Now what happens if you take D1 complex? For example, we are now calculating the crystal field stabilization energy and the pairing energy. Suppose if you calculate crystal field stabilization energy for a D1 complex in the octahedral case. Now, in the octahedral case, the splitting, I am just writing, the splitting is T2G and Eg. Okay. Now it's a D1 electron. So what will be the crystal field stabilization energy for this electron is that crystal field stabilization CFSE is equal to, I told you that electron occupying T2G level will have minus 4 delta O. that is minus 4 delta into 1 electron plus 0.6 delta, 0.6 EG level. EG level there are no electrons. So the CFSE for the D1 state or D1 orbital is 0.4 delta O. Now let us calculate crystal field stabilization for D2. Again, crystal field stabilization is split into two levels. Okay, this is 2 TG level and EG level. Now you have an electron here, one electron and 2 electrons. Now calculate the crystal field stabilization energy minus 0.4 into 2 plus minus 0.6 into EG level, there are no electron. So you have minus point delta O. Now what happens in the D3 case? Let us take D3 case. D3 also will be split into two levels, T2G and EG. Each orbital dxy will carry one electron, dyz will carry an electron, dxz will carry one electron. Now calculate the CFSE. Minus 0.4 into 3 plus 0.6 into 0, that is equal to minus 1.2 delta. So far we did not have any confusion because now D1, D2, D3, the electrons are singly occupied and electron always prefers to occupy the ground energy levels. Now in this case, evidently the energy of the complex would be less and the decrease in energy, okay, is equal to minus 0.4 delta O. Or if you can convert into dqs, if you are converting into a dqs, then it will be 4 dq. It is called ligand field stabilization energy of the complex. That is, for each electron entering into a T2G orbital, the LFSE will be 4 dq. On the other hand, for each electron entering into the EG level, the destabilization energy would be 6 dq. So we have calculated CFSE for D1, D2, D3. There is no point of confusion in this case. Now what happens if you are taking D4 state? If you are calculating CFSE, calculate CFSE, that is crystal field stabilization energy for D4 electrons, D4 system. Now onwards a confusion arises in our heart whether the fourth electron will enter into the T2G level. This is the 5 orbitals. This is EG and T2G. D4 system. First 1 electron, 2 electron, 3 electrons you have equally filled into a ground energy level dxy, dyz and dxz. Now the fourth electron either can enter into a EG level, or can get paired with the dxy in the T2G level. That depends upon the nature of the ligand. Okay, I have mentioned to you that according to the nature of the ligand, the complex can form either low spin complex or high spin complexes. Low spin complexes means the splitting energy is very high and the electron is forced to pair up in the ground energy level. Okay, so now in the case of D4 onwards, we need to consider the two ways. One is low energy or low spin complexes. For example, it is not low energy. It is a low spin complexes or high spin complexes. That means weak field ligands or strong field ligand. Suppose if you are taking this D4 system in a strong field ligand, in a strong field ligands. Okay, strong field ligands. Okay, what happens? They form a low spin complexes. Low spin complexes. And you can take another one is weak field ligand. And they form high spin complexes. So depending upon the nature of the ligand, the nature of the ligand, the electron either can go into the EG level or can get paired up with the T2G level. So for example, if you are taking a strong field ligands, in the case of a strong field ligand, the CFSE, the splitting of the CFSE is maximum. The splitting will be maximum. So as a result, what happens? The energy gap between the EG level and T2G level is very high. So the electron doesn't have a sufficient energy to jump into the higher level. So it automatically gets paired in the lower energy level. So in this case, the CFSE is minus 0.4 into 4 electrons plus 0.6 into 0 electrons. Here, since it is a low spin complex and it is a strong field ligand, the magnitude of the splitting is very high. The electron will not be occupying in this level, but rather gets paired up in the T2G level. Hence, you have 1.6 delta O. 1.6 delta O. Now, let us consider the same D4 system in the case of a weak field ligand. I have mentioned to you yesterday, in the case of a weak field ligand, the magnitude of the splitting is very low. The magnitude of the splitting is very low. So, electron, this is very low. Electron has a sufficient energy to jump into the EG level and it will not get paired at the T2G level. So, in this case, the CFSE is minus 4 into, there are only 3 electrons in plus 0.6 into 1 electron, that is equal to minus 1 point plus 1.6 is equal to minus 0.6, minus 0.6. That is the CFSE in the case of a weak field ligand. Now what happens? Here comes a concept of pairing energy. Here comes the concept of pairing energy. Here in this case, the pairing energy, low spin is spin paired, and it is a strong field ligand. Now what is this pairing energy? How will you define this pairing energy? Only we want to know here. Okay, the pairing energy means all the 4 electrons can occupy either T2G level or can jump into the EG level. The actual configuration may be decided based on the delta O and the pairing energy. That is, the energy required to pair the electron with one another. Is called pairing energy. In this case, the magnitude of splitting is very high. You can see that in the strong field ligand case, the magnitude of splitting is very high. So the pairing energy is not sufficient for the electron, pairing energy is less. So what happens? The lower energy, it will make use and get paired up here. So the magnitude is very high. The splitting of the magnitude is very high. So this is called electron pairing energy. So in this case, when we calculate the CFSE, we need to also to sum up the pairing energy with the CFSE to CFSE. Okay, so here there is a one electron is getting paired. So the total CFSE of this complex is not only because of the electrons that are occupying, but also the energy required by an electron to get paired also should be considered. So in this case, one electron is getting paired, so you need to write 1 EP along with the CFSE. Okay, this is the concept of pairing energy. It will be little more clear if you go for the D5 system. Now let us consider D5 system. Okay, D5 system. Now D5 also has, in the case of a strong field ligand and low spin complexes only we are saying T2G and EG. Okay, it is EG, T2G. The magnitude of splitting is very high than the pairing energy. So what happens? Electron will not jump into the higher level. Rather, it gets paired up in the lower level. So here when you calculate the CFSE is equal to 0.4 into there are 5 electrons plus 0.6 into there are no electrons in the EG level 0, that is equal to 2.0 delta O plus there are 2 electrons which are paired. So plus 2 EP is the pairing energy here. Okay, in this case the pairing energy is greater than the splitting, magnitude of splitting. So in this case delta O is less than the magnitude of splitting. That's why what happens, the pairing energy is sufficient for an electron to jump into the higher levels. So in this case, if you are taking in the weak field case for the D5 system, again you have T2G and EG. There are 5 electrons, 1, 2, 3. The magnitude of splitting is less than the pairing energy. So electron will jump into the higher levels. So in this case, the CFSE is equal to 0.4 into 3 plus 0.6 into 2, that is equal to minus 1.2 plus 1.2, that is equal to 0. That is equal to 0 here. Now let us consider same way D6 system. Consider D6 system. Okay. EG, T2G. Here delta O is greater than pairing energy. The magnitude of splitting is very high. So the pairing energy is not sufficient for electron to jump into the higher level. So electron gets paired in the ground level itself. Okay. Now what happens here? Minus 0.4 into 6 plus 0.6 into 0, that is equal to minus 0.24 delta O plus there are 3 electrons which are getting paired. So plus 3 EP. Okay, this is the Now in this case we can write as a 3 EP, but it is not 3 EP. There are only 2 electrons which are jumping into the 2 electrons should be occupied in the EG level. But instead of occupying the EG level, the 2 electrons will have to go to the EG level. But instead of occupying at the EG level, the 2 electrons are occupying in the ground level. That is why it is known as the 2 EP. There is a possibility of the 2 electrons to go into the EG level. Instead of that, 2 electrons are occupying in the T2G level. So the pairing energy will be of 2 EP. Again, let us consider the same system in the high spin complexes. Okay, now D6. Here, the magnitude of splitting is less than the pairing energy. So what happens? The energy is sufficient for a molecule jump into the higher level. 1, 2, 3, 4, 5, 6. You see there are only 2 electrons that are paired. So it is 2 EP. So in this case, the magnitude of the CFSE is equal to 0.4 into 4 plus 0.6 into 2, that is equal to minus 1.6 plus 1.2, that is equal to minus 0.4 delta O. Minus 0.4 delta O. Now let us consider in the same way D7 system also. D7 system. Okay, there are 7 electrons. There are EG levels. There are 3 T2G levels. We all of us know that here magnitude of splitting is greater than the pairing energy. So you need 7 electrons. 1, 2, 3. Okay. Then what happens? All electron gets paired up first here. Then only 1 electron goes up. So, one electron which has to go up has been paired here, Okay, so as a result you calculate minus 4 into 6 plus 0.6 into 1. That is equal to minus 2.4 plus 0.6, that is equal to minus 1.8 delta O plus 1 electron is supposed to go to the EG level, but instead of going, it has been paired up at the ground level. So the EP, 1 electron, 1 pairing energy will be added to the total CFSE. Here, when you write the high spin complexes, you can easily calculate the pairing energy. Okay, EG level, T2G level. Here pairing energy is great. So 1, 2, 3, 4, 5, 6, 7. So instead of that 1 electron is only paired. That's why here you wrote as 1 pairing energy. Here you have minus 0.4 into 5 plus 0.6 into 2. That is equal to 0.20 plus 1.2 is equal to minus 0.8 delta O. So this is the concept of pairing energy. Now let us consider for the complexes of D8. Now what happens in the concept of D8? We also have 1, 2, T2G level and EG level. Now all the electrons should be paired up here. Okay, though it is paired up, there are sufficiently electrons are there in the system. So what is the difference between the high spin complexes? That is minus 0.4 into 6 plus 0.6 into 2, 1.2 minus 1.2 delta O. There is no concept of pairing energy because electrons are sufficient. First singly occupied, then only the pairing has taken place. Okay, now in the case of, so there are no high spin and low spin. Can you arrange this in a this is the low spin complex. This is the low spin complex. Can you arrange this as a high spin complex? No. First you need to arrange the electrons in the ground level paired, then only it goes. There is no high spin for these complexes. Same with D9 system if you take. D9 system also if you take, there is no high spin and low spin for the D8 and D9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 6, 7, 8, 9. So there is no much pairing for this system. So as a result, what you have here, the CFSE is minus 4 into 6 plus 0.6 into 3, that is equal to minus 2.4 plus 0.8, that is equal to minus 0.6 delta O. There is no concept of low spin and high spin here. There is no concept of pairing energy. Same with D10 system, if you take D10 system also, e.g. T2G 2, 3, 4, 5, 6, 7, 8, 9, 10. Here also you can calculate CFSE, it is delta O. So this is the concept of occupancy of d orbitals by electrons in the octahedral cases. Octahedral complex now both the high spin and low spin. Only in the case of D4, D5, D6, D7 only we have calculation of. Only in the case of D4, D5, D6, D7 only shows and difference of CFSE along with electron pairing energy. Okay, whereas in the D1, D2, D3, D8, D9, D10, there is no concept of pairing energy.